Right now, somewhere aboard a spacecraft moving faster than any vehicle in human history, an astronaut looks back toward a small yellow star and cannot find the planet orbiting it. Not because the planet has vanished, because at 2.8 billion miles away, sunlight itself needs over 4 hours just to make that crossing. One direction, at the fastest speed anything can travel. A phone call home would take over 8 hours to get an answer. But here is the detail almost nobody talks about when they imagine reaching Neptune. It was never really about the distance out. It's about what that distance quietly does to a human being. Long before anyone brings up the question of coming home. Make yourself comfortable. Let's begin. That astronaut is not a character in a story we're inventing tonight. The physics behind that moment has already been proven, in full, by a machine that made the crossing itself. Its name was Voyager 2, and it remains, to this day, the only human-built object that has ever reached Neptune. No spacecraft has gone back since. No human being has gone at all. So before we go any further, it's worth being honest about what kind of question this really is. This is not a story about whether we could survive the trip to Neptune. Survival, in the narrow sense, might be solvable, given enough time, enough engineering, enough decades of careful work. What we're really asking is something quieter and, in its way, harder to sit with. What happens to a person, and to everything that person carries with them, once a distance that large has actually been crossed? Not imagined, not modeled, crossed. Consider what crossed even means at this scale. Neptune orbits the Sun at an average distance of about 2.8 billion miles, nearly 30 times farther from the Sun than Earth is. To put that in human terms, if the distance from the Sun to Earth were the width of a single sheet of paper, the distance to Neptune would stretch nearly the length of a football field. That is the gap Voyager 2 closed, slowly, patiently, using gravity itself as a kind of ladder, swinging past Jupiter, then Saturn, then Uranus, borrowing a little momentum from each giant planet along the way, before finally reaching Neptune in August of 1989, 12 years after it left Earth. No person aboard, no return leg ever planned. It was built to go outward, gather what it could, and keep going outward forever. That distinction matters more than it sounds like it should. Voyager never had to solve the problem this video is actually about. It never had to keep a heart beating, a mind intact, a body fed and warmed and shielded for over a decade in the dark. It never had to come home. A human mission would have to do both of those things at once. And as we'll see, those two requirements do not simply add together. They multiply against each other in ways that quietly rule out almost everything we currently know how to build. But before we can understand why the return trip becomes the real obstacle, we need to understand something more basic. We need to understand how humanity even came to know Neptune was there in the first place. Because the story of how this planet was found is, in its own way, a story about the limits of human reach and the limits of human patience, nearly 200 years before anyone dreamed of sending a person there at all. Neptune's story does not begin with a telescope. It begins with an irregularity. In the early 1800s, astronomers watching the planet Uranus noticed something that refused to behave. Uranus kept drifting slightly off the path that Newton's laws said it should follow, tugged, ever so faintly, by something unseen. For decades, this was treated as a curiosity, an error in observation, perhaps a flaw in the math itself. Then, in 1845, a French mathematician named Urbain Le Verrier decided to take the irregularity seriously. He did not build a bigger telescope. He did not travel anywhere. He sat with the numbers, month after month, and worked backward from the wobble in Uranus's orbit toward the mass and position of a planet no human being had ever seen. By the late summer of 1846, Leverrier believed he knew almost exactly where that planet would be. He wrote down a set of coordinates and mailed them to the Berlin Observatory, to an astronomer named Johann Galle. On the night of September 23, 1846, Galle pointed a telescope at the patch of sky Leverrier had described, working alongside a younger astronomer, Heinrich d'Arrest. In under an hour they found it, a world, later named Neptune, sitting within about 1 degree of the exact position a man in Paris had calculated using nothing but pencil, paper, and the patient logic of gravity. It remains, to this day, the only major planet in our solar system discovered through mathematics before it was ever seen through glass. In simple terms, what this means is that humanity reached Neptune with the mind almost a century and a half before it reached Neptune with a machine. Leverrier never left his desk. He never needed to. Numbers can cross 2.8 billion miles instantly, the moment the right equation is written down. Bodies cannot. And that gap between what the intellect can calculate and what the body can actually survive is the real subject of everything that follows in this story, because the calculation that found Neptune took months. The journey to actually reach it would take 12 years for an unmanned probe with no life to sustain, and considerably longer, by every serious estimate, for anything carrying a human being who needed to eat, breathe, and one day, perhaps, come home. Leverrier's discovery also reveals something quieter about how humans relate to distance. We are a species that reaches with our minds far more easily than we reach with our hands. We had accurately calculated Neptune's mass, its orbit, its position in the sky, more than a century before a single spacecraft ever photographed its clouds. And we would go on, for another 143 years after that first discovery, simply waiting for engineering to catch up to arithmetic. That wait ended in the summer of 1989, when a small robotic explorer, already 12 years into its journey, finally closed the gap that Leverrier had only ever closed on paper. Voyager 2 left Earth on August 20, 1977, launched from Cape Canaveral aboard a Titan III rocket, carrying a little over 1,500 pounds of instruments, cameras, and a golden record etched with sounds and images meant to explain humanity to whatever might one day find it drifting between the stars. Nobody aboard, of course. There has never been anybody aboard. But everything about how it reached Neptune tells us something essential about what a human journey to that same planet would actually require. The spacecraft did not fly there in a straight line. It used something called a gravity assist, borrowing a small amount of momentum from Jupiter in 1979, then Saturn in 1981, then Uranus in 1986, each flyby bending its path and adding to its speed like a slingshot released in careful stages. This was not a shortcut chosen for convenience. It was closer to a necessity. Chemical rockets, even the best ones humanity has ever built, cannot generate enough thrust on their own to reach the outer solar system quickly. They needed help from the planets themselves. By the time Voyager 2 approached Neptune in August of 1989, it was traveling at roughly 42,000 miles per hour relative to Earth, a velocity gained not from its engines alone, but from more than a decade of careful gravitational borrowing. To put that speed in human terms, 42,000 miles per hour is more than 30 times faster than a commercial airliner cruising at altitude. At that speed, Voyager 2 could have circled the entire Earth in under 35 minutes, and it still took 12 years to reach Neptune, not because the spacecraft was slow by any ordinary measure, but because the distance it needed to cross was simply that vast. 12 years for a machine that needed no food, no water, no breathable air, no protection beyond what its instruments required to keep functioning. 12 years for something that never once had to consider a way home. This is the quiet detail that separates every robotic mission humanity has ever sent outward from any theoretical human one. Voyager 2's mission planners never had to design a return trajectory. They never had to calculate how much additional fuel it would take to slow the spacecraft down, reverse its direction, and send it back across that same 2.8 billion miles a second time. The mission was built, from its very first design sketch, to be one-directional, outward, and then further outward still. Today, more than 4.5 decades after launch, Voyager 2 is still traveling, now well beyond Neptune, well beyond the orbit of any planet, moving through the outer edges of what astronomers call the heliosphere, the bubble of influence our sun casts against the rest of the galaxy. A human mission could not be built this way. A human mission would need to solve two enormous problems that Voyager never had to face: keeping a living body intact for a journey of that length, and finding a way to bring that body home again. And it's worth pausing here on just how much harder the second problem turns out to be than the first. Even setting aside the question of travel entirely, even imagining a crew already standing on Neptune's icy moon Triton, fully arrived, fully safe, there remains a barrier that no amount of engineering can currently remove. It has nothing to do with rockets or fuel. It has to do with light itself, and the strange fixed speed limit written into the fabric of the universe. Light travels at roughly 186,000 miles per second, the fastest anything can move. From the Sun to Earth, that journey takes about 8 minutes, which is why, in a very real sense, we never see the Sun as it is right now. We see it as it was 8 minutes ago. Neptune sits so much farther out that the same principle stretches into something almost unrecognizable. Depending on where Earth and Neptune happen to be in their respective orbits, light takes somewhere between 4 hours and just over 4 hours to cross the distance between them. Not 4 minutes, 4 hours. Consider what that means for something as simple as a conversation. A radio message sent from Neptune, traveling at the absolute fastest speed physics allows, would take over 4 hours just to arrive at Earth. If someone on Earth responded immediately, that reply would take another 4 hours to travel back. A single exchange, one sentence sent and one sentence answered, would take more than 8 hours to complete. In simple terms, there is no such thing as a phone call across this distance. There is no such thing as a conversation in the way we understand the word. There is only a message sent into a gap and an answer that arrives long after the question has stopped feeling urgent. This is not a limitation of current technology. It is not something a better radio antenna or a stronger signal could ever fix. The 4-hour delay is built into the geometry of the solar system itself, the same way it takes 8 minutes for sunlight to warm your skin on a summer afternoon, whether you like it or not. Mission controllers who worked with Voyager 2 during its 1989 flyby lived this delay directly. Every image the spacecraft captured of Neptune's clouds, every measurement of its rings, took over 4 hours to arrive at Earth, already old by the time anyone on the ground could see it. And Voyager was a machine sending data. A human crew would be sending something closer to a life, news of an illness, news of a birth. A simple, ordinary sentence like, "I miss you," launched into the dark, arriving hours later to an Earth that has already moved on without knowing it was said. If speaking to Earth becomes this slow, this stretched, this quietly impossible to do in real time, then a harder question begins to take shape. What happens to actually seeing Earth? Not hearing from it, seeing it, the way the astronaut in our opening scenario tried to, looking back toward a small yellow star and searching for the world they left behind. Here is the detail that gives this video its title, and it is worth sitting with slowly, because it is easy to misunderstand at first hearing. From Neptune, Earth does not disappear because it moves too far away to exist. It disappears because of where it sits relative to the Sun, and because of what light does to human eyes and human instruments when it is forced to compete with something far brighter nearby. From Earth, we sometimes struggle to see Mercury, even though it is one of our nearest planetary neighbors, simply because Mercury orbits so close to the Sun that its light gets lost in the glare. The same geometry, stretched across a much larger stage, applies to Earth as seen from Neptune. Earth orbits close to the Sun, relative to Neptune's enormous distance out. From that far away, Earth and the Sun sit so close together in the sky that Earth's faint reflected light is swallowed by the Sun's overwhelming brightness for much of Neptune's long orbital year. Seeing Earth from Neptune would not simply mean looking up. It would mean waiting for the rare moment when the geometry allowed it, and even then, using instruments built specifically to block out the Sun's glare in order to find one faint point of light beside it. We already know this is possible because it has been done, once, deliberately, and the story behind it says something worth pausing on. In February of 1990, after completing its planetary flybys, Voyager 2's twin spacecraft, Voyager 1, was commanded to turn its camera back toward the solar system it had just left and take a series of photographs. From a distance of roughly 3.7 billion miles, far beyond Neptune's orbit, one of those photographs captured Earth as a single point of light, less than a pixel across, suspended in a scattered ray of sunlight. It became known as the pale blue dot. It required careful timing, a precisely angled camera, and a shaded lens, because even from that distance, the Sun's glare threatened to erase Earth from the image entirely. What this means in practice is that never seeing Earth again is not a poetic exaggeration built for a video title. It is closer to a literal description of the viewing conditions a human being would actually face, standing on Neptune or one of its moons, trying to find their home world with the naked eye. Most of the time, it would not be visible at all, lost in the brilliance of the Sun sitting beside it. And on the rare occasions when the geometry allowed a glimpse, using the right instrument at the right moment, what they would be looking at would not be Earth as it is. It would be Earth as it was, 4 hours earlier, the light having spent that entire time crossing the gap between the two worlds. A photograph, in other words, not a window. That distinction between a window and a photograph is not just a technical footnote. It quietly answers something the title of this video has been circling from the very beginning. But to understand why it matters this much, it helps to see, for a moment, how a group of real people once sat with this exact distance, waiting, 4 hours at a time, for a single image to arrive. In the last week of August 1989, at the Jet Propulsion Laboratory in Pasadena, California, a room full of scientists and engineers sat in front of banks of computer monitors, waiting. Voyager 2 was making its closest approach to Neptune, coming within about 3,000 miles of the planet's north pole, close enough to capture the sharpest images of the ice giant that humanity had ever seen or has seen since. But nobody in that room could watch it happen in real time. Every image the spacecraft captured had to travel over 4 hours across empty space before it reached Earth at all. So they waited. 4 hours for a single photograph. 4 hours to know whether the camera had captured what it was aimed at, whether the storm called the Great Dark Spot had been framed correctly, whether Neptune's faint rings had shown up clearly enough to confirm what astronomers had only suspected before. The engineers who built and flew Voyager 2 described that week as electric, tense, filled with a strange kind of patience that had no equivalent in ordinary life. You did the work, you sent the command, and then you simply sat, for hours, with nothing to do but wait for light to finish its crossing. Consider what that delay was for. It was for photographs, still images of clouds and rings, and a distant, icy moon named Triton, which Voyager 2 also passed that week. recording a surface colder than almost anywhere else ever measured in the solar system, colder than -390 degrees Fahrenheit. The scientists in that room were waiting 4 hours at a time for pictures of a place no human being had ever seen up close. And even that felt, to the people living through it, like an almost unbearable stretch of patience. Now imagine that same 4-hour gap, not carrying a photograph, but carrying a person's entire remaining connection to Earth. Not a picture of a storm, but a message from a spouse, a child, a friend, sent outward into the dark and arriving hours later to someone who has been living, in every practical sense, alone. The JPL engineers in 1989 endured that wait for a single week, driven by excitement, surrounded by colleagues, with the certainty that ordinary life on Earth was still waiting for them the moment they walked out of the building. A crew standing where Voyager 2 once flew would face that same 4-hour gap, not for a week, but for the entire span of the mission, without the comfort of knowing it would end soon, and without anyone beside them who remembered what an ordinary Tuesday on Earth even felt like anymore. That comparison between a week of excited waiting and years of isolated waiting begins to hint at something larger than the physics we've covered so far. Because the distance to Neptune is not only a problem of time and light, it is just as much a problem of what kind of machine could even survive attempting the crossing with a living crew aboard. And that question starts, as most questions about spaceflight do, with propulsion. Every rocket humanity has ever launched, from the first tentative flights of the space age through to the most advanced vehicles flying today, relies on the same basic principle: burn a fuel, expel the exhaust at high speed out the back, and let the resulting push carry the vehicle forward. This is called chemical propulsion, and it has carried every human being who has ever left Earth's atmosphere. It is also, by a wide and well-understood margin, nowhere near powerful enough to carry a person to Neptune within a survivable amount of time, let alone bring them back. The core limitation is something engineers call specific impulse, a measure of how efficiently a rocket converts its fuel into thrust. Chemical engines, even the best ones ever built, sit near the low end of what's physically achievable. In simple terms, chemical fuel simply cannot pack enough energy into a small enough mass to accelerate a spacecraft to the kind of speeds that would make a Neptune mission practical using thrust alone. This is precisely why Voyager 2 did not fly to Neptune in a straight line, powered the whole way by its own engines. It couldn't have. Instead, mission planners built its entire trajectory around gravity assists, borrowing momentum from Jupiter, Saturn, and Uranus in sequence, using the planets themselves as a kind of relay system, because chemical propulsion alone was never going to be sufficient. Consider what that means for a human mission. Voyager 2 weighed a little over 1,500 pounds, mostly instruments, and a small amount of fuel for course corrections. A vehicle capable of keeping a human crew alive for a Neptune mission would need to carry breathable air, drinking water, food, radiation shielding, redundant life support systems, and enough structural mass to survive over a decade in transit. All of that mass would need to be accelerated using the same chemical propulsion that already struggled to move something as light as Voyager. No serious space agency has ever proposed a human-crewed chemical rocket for a Neptune mission, not because nobody has thought about it, but because the mathematics rule it out before the conversation can even properly begin. This is why, when scientists and engineers do discuss what a crewed mission to the outer solar system might actually require, the conversation moves almost immediately away from chemical propulsion entirely, towards something fundamentally different, not a bigger version of the rockets we already have, but an entirely different way of generating thrust, one that trades the familiar, well-tested limitations of chemical fuel for a set of possibilities that remain, even now, mostly theoretical, mostly experimental, and entirely unproven at the scale a mission like this would demand. The most seriously studied alternative to chemical propulsion is called nuclear thermal propulsion, and the idea behind it is easier to picture than the physics might suggest. Instead of burning fuel to create thrust, a nuclear thermal engine uses a small reactor to heat a propellant, usually hydrogen, to extremely high temperatures, then expels it out the back of the vehicle at far greater efficiency than any chemical reaction can achieve. NASA and the Defense Advanced Research Projects Agency have both invested in this technology in recent years, including a joint program known as DRACO, aimed at testing a nuclear thermal engine in orbit within the next several years. In simple terms, what this technology offers is a real, meaningful improvement in efficiency over chemical rockets, potentially cutting travel times for missions within the solar system significantly compared to conventional propulsion. This matters. It represents genuine, funded, actively pursued engineering, not speculative fiction. But it is important to be honest about what this technology does and does not solve. Even optimistic estimates for nuclear thermal propulsion describe a mission to Mars, a destination vastly closer than Neptune, as taking months rather than years. Extending that same technology, still in its early testing phases, out to a destination 30 times farther from the Sun than Earth, remains a proposal, not a proven capability. No nuclear thermal engine has ever propelled a spacecraft, human or robotic, beyond Earth orbit. What this means in practice is that even our most promising near-term propulsion technology shrinks the transit time to Neptune. It does not eliminate the underlying problem this entire video is built around. A faster engine gets a crew there in less time, perhaps meaningfully less time than the 12 years Voyager 2 required. But every proposal for advanced propulsion, however promising, still describes a journey measured in years, not weeks, and still requires enough fuel and reaction mass to make the return trip as well as the outbound one. And it is here that the conversation runs into a wall that no engine design, however advanced, can fully escape. Because getting to Neptune and getting back from Neptune are not the same problem doubled. They are a problem that compounds against itself, in a way that quietly explains why so few serious mission proposals for the outer solar system ever seriously plan for a return leg at all. There is a piece of mathematics at the heart of every spaceflight ever attempted, discovered by a Russian schoolteacher named Konstantin Tsiolkovsky more than a century ago. And it explains, more clearly than almost anything else in this story, why the return journey from Neptune is not simply a second version of the outbound one. It is a harder problem entirely. Here is the idea, in familiar terms. A rocket has to carry all of its own fuel with it, for the entire journey, from the moment it launches until the moment it no longer needs to burn anymore. Every extra pound of fuel adds weight, and that added weight itself requires more fuel to move it, which adds more weight, which requires still more fuel to move that. This is sometimes called the tyranny of the rocket equation, and it means that fuel needs do not grow in a simple, steady line. They grow the way a snowball grows rolling downhill, each addition making the next one heavier and more expensive than the last. Now apply that to a Neptune mission. A one-way trip requires enough fuel to accelerate a crew and their vehicle up to a useful speed, and enough shielding and life support to survive the years it takes to get there. A round trip requires all of that, plus enough additional fuel to decelerate upon arrival, enough fuel to accelerate back out of Neptune's gravitational influence for the return leg, and enough fuel again to slow down safely upon reaching Earth. In simple terms, every kilogram of return fuel is a kilogram that has to be carried, accelerated, and protected for the entire outbound journey first, before it is ever used. The vehicle does not simply need twice the fuel of a one-way mission. Because of how the rocket equation compounds, It can require dramatically more than that, depending on the propulsion method involved. This is the honest, unglamorous reason why so many serious engineering discussions about crewed missions to the outer solar system, when they are candid about the mathematics, quietly treat the return leg as the far harder half of the problem, if they treat it as solvable at all. It is also why, when NASA and independent researchers have discussed crewed missions to destinations as comparatively close as Mars, some published proposals have seriously examined one-way mission architectures, not as tragedy, but as an honest response to what the fuel math actually demands. Neptune sits roughly 60 times farther from the Sun than Mars does. Whatever pressure that mathematics puts on a Mars mission, it does not simply grow at Neptune's distance. It compounds, the same way the fuel itself does. But fuel and mathematics are only half of what makes this journey so difficult, because even if every equation could somehow be solved, even if a vehicle existed with enough fuel to make the full round trip, there remains a separate and equally unforgiving problem. What that 11-year, or 20-year, or 30-year journey would actually do to the human body carrying it out. Earth has a quiet, invisible advantage that almost nobody thinks about until they leave it. Our planet sits inside a magnetic field, generated deep within its molten core, that wraps around the Earth like an invisible shield and deflects the vast majority of dangerous radiation streaming toward us from deep space. The astronauts aboard the International Space Station, orbiting a few hundred miles up, still benefit from most of this protection, because they remain within Earth's magnetosphere. A crew traveling to Neptune would not. The radiation in question is called galactic cosmic radiation, high-energy particles flung across the galaxy by exploding stars and other violent cosmic events, traveling near the speed of light until something gets in their way. Outside of Earth's protective field, this radiation passes through spacecraft hulls, through equipment, and through human tissue, essentially unimpeded by anything short of very heavy shielding. NASA has studied this extensively, tracking the cumulative radiation exposure of astronauts across their careers, and setting strict lifetime limits based on that research. Because the accumulated damage from galactic cosmic rays raises long-term risks of cancer and other serious health effects, the longer a person remains exposed. In simple terms, this is not a risk that appears suddenly, like an explosion or a mechanical failure. It is a slow, cumulative erosion, radiation damage stacking, day after day, month after month, for the entire duration of a mission that offers no shelter from it beyond whatever shielding the spacecraft itself provides. Current NASA astronaut career radiation limits are calculated specifically because agency researchers know that longer missions in deep space accumulate exposure that Earth-based life, and even low-orbit life aboard the space station, never has to contend with. A journey to Neptune, lasting many years each way, would mean living inside that exposure continuously, for longer than almost any mission concept currently studied. To put this in human terms, consider that even proposed multi-year Mars missions, a journey vastly shorter than one to Neptune, already push close to or beyond currently accepted astronaut radiation limits, according to published NASA and independent research on the subject. A Neptune mission, multiplying that transit time several times over, would ask a human body to absorb a radiation dose far beyond anything currently considered acceptable for any astronaut, on any mission, at any point in the history of human spaceflight. And galactic cosmic radiation is only the steady, background version of this danger. There is a second kind, less constant, but far more sudden and far more dangerous when it arrives. Beneath the slow, constant hum of galactic cosmic radiation lies a second, sharper danger, one that arrives without much warning and can deliver, in a matter of hours, more radiation than months of ordinary background exposure combined. These are called solar particle events, sudden bursts of high-energy particles ejected from the Sun during solar flares and coronal mass ejections, capable of flooding a spacecraft with radiation intense enough to cause acute radiation sickness in an unshielded crew. NASA and other space agencies take this threat seriously enough that deep space mission designs typically include what engineers call a storm shelter, a small, heavily shielded compartment where a crew can retreat during a major solar event, often using stored water or other dense materials to absorb the incoming particles until the danger passes. This works reasonably well for missions closer to the Sun, where solar events are more predictable and warning times, while short, are at least measured in hours. Consider what happens to that warning system at Neptune's distance. A solar particle event detected near Earth would take over 4 hours just for the warning itself to reach a Neptune-bound crew, by which point the radiation from that same event, traveling at nearly the speed of light, may have already arrived or already passed. In simple terms, the same 4-hour communication delay that severs conversation between Neptune and Earth also strips away most of the advance warning a crew would normally rely on to protect themselves from a solar storm. Shielding still helps. A storm shelter would still reduce the danger, but the layer of protection that Earth orbit missions depend on, real-time warning from solar observatories, effectively disappears at this distance, replaced by whatever the spacecraft's own instruments can detect and respond to, alone, without guidance from home. What this means, taken together with the slow accumulation of galactic cosmic radiation, is that a Neptune-bound crew would face 2 separate and compounding threats to the body itself, one chronic and one sudden, for the entire multi-year duration of the mission, using shielding technology that has never been tested across a time frame this long, at a distance this far from any source of real-time support. Even a perfectly engineered hull with the best shielding available addresses only the body. It offers nothing at all for a separate and equally real danger, the one that begins not in the cells, but in the mind. Long before anyone seriously studied what a multi-year mission to Neptune might do to the human mind, NASA had already begun learning what shorter versions of that same isolation could do. The lessons started small. During the Apollo missions, astronauts orbiting the Moon experienced something no human being had ever felt before. A specific, documented period on the far side of the Moon when radio contact with Earth was completely severed, blocked by the Moon's own mass. For roughly 45 minutes at a time, an Apollo astronaut was more alone than any human being in history had ever been, cut off entirely from every other living person. 45 minutes. That is the entire span of isolation NASA had real, lived, documented experience with, before later missions began asking harder questions about longer separations. Since then, researchers have studied the psychological effects of confinement and isolation far more directly, through long-duration missions aboard the International Space Station and through ground-based analog missions such as HICs in Hawaii and Mars 500 in Russia, simulated missions lasting many months, designed specifically to study how small, confined crews respond to prolonged isolation without real escape. These studies have documented real, measurable effects, including disrupted sleep patterns, shifts in mood and motivation, and strain on group dynamics within small, enclosed crews over time. Now, for a moment, put yourself inside that research. Not for 45 minutes. Not for 6 months in a habitat in Hawaii, with occasional outside contact still available, and an actual return to ordinary life waiting at the end of a fixed, known date. Imagine instead years spent aboard a vessel with a crew who cannot leave each other's company, communicating with Earth only through messages that take 4 hours to arrive and 4 hours to answer, with no 45-minute gap in contact, but rather one that never fully closes, stretched across the entire remaining span of the mission. The analog missions NASA has studied, HICs, Mars 500, even long-duration stays aboard the space station itself, all share one detail that a Neptune mission would not have. Earth remained close. A crew member could, at least in principle, imagine turning back. The isolation was real, the psychological strain was measurable and documented, but it existed inside a boundary, a known endpoint, a world still genuinely reachable if something went wrong. A mission to Neptune removes that boundary entirely, not as metaphor, a simple physical fact built from the numbers we've already covered. 4 hours of light lag in each direction, a body already absorbing radiation no astronaut has ever been asked to absorb. And now, added to both of those, a level of isolation that no analog mission on Earth, however carefully designed, has ever been able to fully simulate, because no analog mission on Earth has ever actually taken Earth away. There is a detail buried inside the 4-hour delay that becomes harder to sit with the longer you think about it. It is not simply that conversation slows down, it is that the very meaning of a message begins to decay across the distance it has to travel, in a way that has nothing to do with signal strength or technology, and everything to do with time itself, passing differently for the sender and the receiver. Consider a message sent from Earth to a Neptune-bound crew several years into their mission. It might carry news, a birthday, a promotion, the birth of a grandchild, ordinary details of an ordinary life continuing to unfold. That message takes over 4 hours to arrive. By the time it does, the moment it describes is already old. A reply, if one is sent immediately, takes another 4 hours to travel back. In simple terms, a single exchange of news takes the better part of a working day to complete, and that is only the mechanical delay. Layer that same gap across a mission lasting many years, and something else begins to happen. The Earth a departing crew member carries in memory, the specific faces, the specific voices, the specific rhythm of a specific life, begins to drift further and further from the Earth that actually continues on without them. To put this in human terms, imagine a crew member who leaves Earth with a teenage child. A round-trip mission to Neptune, using even the most optimistic proposed propulsion timelines currently discussed by researchers, would very plausibly keep that crew member away for the greater part of a decade, if a return were achievable at all. The child who was 15 when they left may be approaching 30 by the time any reunion becomes possible. Letters exchanged across 4-hour gaps cannot capture the accumulation of an entire adolescence, an entire adulthood beginning, an entire life reshaping itself in the absence of a parent who is, at every moment, simultaneously present in memory and inaccessible in fact. This is not a failure of communication technology. Faster radios would not fix it. Better compression, clearer signal. None of it touches the underlying problem, because the problem was never about clarity. It was always about the 4 hours themselves, repeated across years, compounding the way distance always compounds when nothing can move faster than light allows. What this means in practice is that a crew returning from Neptune, if a return is even part of the mission's design, would not be returning to the world they left. They would be returning to a different version of it, shaped by years of changes experienced only second-hand, through messages already hours old by the time they were understood. And that emotional cost, real as it is, sits on top of something colder and more physical, something measured not in memory, but in bone density and muscle mass. A set of changes that begin the moment a human body leaves Earth's gravity and do not fully reverse, for some crew members, even after they return. Long-duration spaceflight leaves a measurable signature on the human body, and NASA has documented this signature carefully across decades of research aboard the International Space Station, where astronauts have flown missions lasting close to a year at a time. The most consistent finding involves bone density. In microgravity, without the constant resistance of Earth's gravity pulling against the skeleton, bones begin losing density at a documented rate, particularly in weight-bearing areas like the hips and spine, even with rigorous daily exercise routines designed specifically to slow the loss. Muscle mass follows a similar pattern, atrophying steadily in an environment where simply standing, walking, and lifting no longer require the effort they do on Earth. In simple terms, the body adapts to its environment, and it adapts honestly. Muscle and bone that go unused, even for reasons entirely outside a person's control, begin to disappear, because maintaining them costs the body energy it no longer seems to need. Astronauts returning from missions aboard the space station undergo extensive rehabilitation, often for months, to rebuild strength and bone density that microgravity quietly took from them. Some documented effects, particularly certain vision changes associated with fluid shifts in microgravity, known as spaceflight-associated neuroocular syndrome, have been observed to persist in some astronauts even after their return to Earth. Consider what this means at the scale of a Neptune mission, the longest continuous human spaceflight on record, held by cosmonaut Valery Polyakov aboard the Mir space station, lasted just over 14 months, and even that mission required a lengthy, carefully managed recovery afterward. A Neptune mission, using even the most optimistic transit estimates discussed in serious engineering proposals, would keep a crew in space for years, not months, exposed to microgravity conditions for a duration many times longer than any human being has ever endured, followed, if a return leg were completed at all, by a readjustment to Earth's gravity that no existing rehabilitation program has ever needed to plan for. What this means in practice is that even in the most successful, most carefully engineered version of this mission, one where every propulsion problem is solved, every radiation risk is shielded, every psychological strain is somehow managed, the body that eventually returns to Earth would not be the same body that left it. Bone density lost over years in transit may not fully return. Muscle rebuilt through rehabilitation may never match what departed. The astronaut stepping back onto Earth's surface, if that moment ever arrived, would be doing so inside a body reshaped by a journey longer than any human body has ever been asked to survive. And this is where the mathematics of the mission and the mathematics of a human life finally meet directly, because a Neptune round trip does not just strain a body. Depending on how it is designed, it can consume a significant portion of the working years a person has to give. Sit with this for a moment, because it is the point where every piece of this story finally converges into something personal rather than abstract. Picture yourself as the crew member, not a statistic, not a mission parameter, but a specific person with a specific number of working years ahead of you, deciding whether to accept a seat on a Neptune-bound spacecraft. Serious engineering proposals for crewed missions to the outer solar system, even ones built around optimistic future propulsion technology, typically describe transit times measured in years for the outbound leg alone. Add time spent at Neptune conducting the mission's actual purpose, whatever that purpose might be. Add a return leg requiring its own multi-year transit, burdened by all the additional fuel mass we discussed earlier, fuel that has to be carried, protected, and preserved for the entire outbound journey before any of it is used. Stack those phases together using the most credible propulsion assumptions currently discussed in the research literature, and many proposed round-trip mission profiles stretch toward, or beyond, 2 full decades from launch to return. In simple terms, a person who launches at 35 might not complete the round trip until they are approaching 60, having spent the entire most productive stretch of their working life, the years most people spend building a career, raising children, watching parents age, inside a spacecraft, absorbing radiation no astronaut before them has been asked to absorb, losing bone density no rehabilitation program has ever needed to fully address. This is not a dramatic exaggeration built for effect. It is the plain arithmetic of transit time added to transit time, applied to an ordinary human lifespan. What this means in practice is something mission architects have had to reckon with honestly, even for destinations far closer than Neptune. When NASA researchers and independent engineers have examined crude mission concepts to Mars, some published proposals have seriously discussed one-way mission architectures, not because scientists want to abandon astronauts, but because the fuel mathematics and time mathematics, taken together, make a round trip so costly that some researchers have asked whether a one-way mission might be the more honest, more achievable version of the goal. Mars sits a fraction of the distance to Neptune. Whatever pressure led some researchers to consider one-way concepts for Mars does not simply apply with equal weight at Neptune's distance. It applies with far more. This is the quiet, uncomfortable place where serious mission planning eventually arrives, once every other problem in this story has been laid out honestly. Not a question of whether the crew could survive the journey. A question of whether coming home was ever really the part of the plan worth designing around in the first place. It is worth being precise about where this idea actually comes from, because it did not begin as science fiction, and it did not begin with Neptune. It began with Mars, the closest planet seriously considered for human crews, and it began with researchers and engineers doing exactly what we've been doing throughout this video, following the mathematics honestly, all the way to wherever it leads. Over the past several decades, a number of researchers, including some working independently of NASA, have published serious academic and engineering proposals examining one-way human missions to Mars. The reasoning behind these proposals is not born from despair. It comes from a clear-eyed look at the mathematics of the rocket equation we discussed earlier, the same principle discovered by Konstantin Tsiolkovsky, applied honestly to a round trip. These researchers argued that the fuel, mass, and cost required to bring a crew back from Mars might be so much greater than the requirements of a one-way mission that a colony-style, non-returning mission could be more achievable sooner than a round trip ever would be. This idea has been discussed publicly and taken seriously within parts of the aerospace engineering community, whatever one's personal view of it. In simple terms, what this reveals is that one-way reasoning is not a fringe idea invented for dramatic effect. It is a documented, published line of engineering thought, applied to Mars, a world where sunlight still arrives in a matter of minutes, where a message home takes only a few minutes to cross the gap, rather than hours. If mission designers have already had to seriously entertain one-way architectures for a world this comparatively close, the same reasoning, extended honestly to Neptune, becomes very difficult to avoid. Neptune sits roughly 60 times farther from the Sun than Mars does. Every pressure that pushed some Mars mission designers toward one-way thinking, the fuel mathematics, the return trip mass penalty, the sheer duration a round trip would demand, exists at Neptune's distance in a far more extreme form. Consider what this means for the astronaut in our opening scenario, looking back toward a star they can no longer easily see their own planet beside. If the mission that sent them there was designed with return as a secondary goal, or no goal at all, then their inability to see Earth again was never really an accident of physics happening to them. It was a condition already present, quietly, in the mission's design, long before they ever left the ground. What remains, once return, is no longer the organizing goal of a mission like this, is not failure. It is simply a different kind of journey, one that asks what a human being becomes when distance stops being something to overcome, and starts being something to live inside, permanently, the way a person might live inside a house rather than pass through a doorway. Out there, at the edge of what our sun can meaningfully touch, the light itself grows tired. Neptune receives roughly 900 times less sunlight than Earth does, a consequence of simple distance, of the same inverse relationship that makes a candle blinding up close and nearly invisible from across a large, dark room. Voyager 2, passing through that dim light in August of 1989, recorded winds tearing across Neptune's atmosphere, faster than anything ever measured on any other planet in the solar system, faster than the speed of sound, moving through clouds of methane that give the planet its deep, quiet blue. Cold beyond ordinary description, Triton, Neptune's largest moon, registered a surface temperature colder than -390 degrees Fahrenheit, one of the coldest places Voyager 2 ever measured anywhere in its journey across the solar system. This is the place a crew member in our story would come to know, not as a destination passed through, but as a kind of permanent address. Not hostile exactly, not in the way a storm is hostile or a collision is hostile, simply indifferent, simply very far away and very quiet and very cold, in the way the space between things is always cold when nothing warm is close enough to matter. And somewhere in that dim blue light, on the rare occasion the geometry allowed it, a crew member might turn a shielded instrument toward a small, pale point of light, sitting close beside the glare of a distant sun. Earth, not gone, never gone exactly, only ever 4 hours in the past, the way a photograph is always of a moment that has already finished happening by the time anyone looks at it. The light reaching that instrument left Earth 4 hours earlier, carrying a version of the planet already slightly out of date, already slightly different from the Earth that continued on, quietly, in the 4 hours since. This is the quiet shape of the answer this video opened with. Not that Earth vanishes, and not that it is destroyed, or lost, or erased. Only that the act of seeing it becomes something closer to remembering it. A photograph mistaken, gently, for a window. A place held always at arm's length, close enough to glimpse on the rare, correctly angled evening, far enough that what is seen was already history the moment the light began its crossing. The astronaut looking back toward that small star, searching for the planet they left, was never really failing to find Earth. They were only ever finding an Earth from 4 hours ago, over and over, for as long as they remained. So we return, gently, to the question this video opened with. Why would the first humans to reach Neptune never see Earth again? Not because the planet ceases to exist, not because some catastrophe erases it from the sky, because at 2.8 billion miles, across a gap that takes light itself over 4 hours to cross, seeing Earth stops meaning what it means here, standing in a backyard, looking up at a sky where everything visible is already old, but only by minutes, only by an amount small enough for the mind to forgive and forget. At Neptune's distance, that forgiveness becomes impossible. Every photograph sent home would show an Earth already 4 hours in its past. Every photograph received from home would show the same delay running in reverse. A crew member could, in principle, look at an image of Earth and correctly say, "That is my planet," and just as correctly say, "That is not what my planet looks like right now," because right now, at that exact distance, does not fully exist between 2 points separated this far. There is only before, and the light still traveling to carry it somewhere else. This is what the mathematics, the mission proposals, the radiation studies, and the honest engineering literature all quietly agree on, once every euphemism is set aside. A journey to Neptune, whatever propulsion eventually makes it possible, asks something of a human being that no journey on Earth has ever asked. Not simply endurance, not simply distance covered. It asks a person to accept that the world they carry in memory will keep moving without them, 4 hours ahead, always, for as long as the mission lasts, whether that mission is measured in years or in something closer to the remainder of a life. And now, for a moment, come back. Not to Neptune, not to the cold, dim light, 900 times fainter than what falls on you right now. Come back to wherever you actually are, tonight. This ordinary distance from everyone you know, somewhere nearby, within minutes, not hours. Someone you love is asleep, or awake, or simply going about an evening that will still be there tomorrow for you to rejoin without a 4-hour delay standing in the way. That is the quiet gift hidden inside a story about impossible distance. Not a warning, not a tragedy, only a reminder of how rare it actually is, how easily overlooked, to live this close to the people who matter to you, in a universe built, mostly, out of distances too large for closeness to survive at all. You are listening to these words from somewhere on Earth, in a room that is, right now, exactly as far from everyone you love as an ordinary evening allows, not 4 hours away, not lost in the glare of a distant sun, close enough that a message sent tonight arrives tonight, close enough that a voice on the phone is still, in every meaningful sense, present. We opened this video with an astronaut looking back toward a small yellow star, searching for a planet they could no longer easily find. By now, that image means something different than it did an hour and a half ago. It was never really about an astronaut at all. It was about what happens when distance stops being something a person crosses and becomes, instead, something a person lives inside. A journey to Neptune, whatever form it eventually takes, whatever propulsion eventually makes it possible, was never simply a story about reaching a planet. It was a story about what gets left behind in the reaching, and how much of a human life and a human self depends quietly on staying close enough to the people who knew you before you left. Somewhere, decades from now, if such a mission is ever attempted, a crew member may stand on a moon so cold that Voyager 2's own instruments struggled to fully register it, and turn a shielded lens toward a point of light beside a distant sun. They will find Earth exactly where the mathematics says it should be, and they will understand, in a way that no amount of preparation on the ground could have fully taught them, that what they are looking at is not a window. It is a photograph, 4 hours old, of a home that kept moving the entire time they were watching for it. Perhaps that is the real difference between a visit and an exile. Not distance, not time, only whether the world you left is still close enough to answer before the question stops mattering. Somewhere tonight, a porch light is switched on for someone walking home. It takes no 4 hours to reach them. It is simply there, waiting, the moment they arrive. You are closer to everyone you love than any astronaut bound for Neptune will ever be again. That, more than any equation in this video, might be worth remembering as you drift, now, towards sleep. The universe is very large, and very cold, and very quiet, in nearly all of the places light has ever touched. But not here, not yet.